Hello everyone, this is Kinshuk here. Today I would like to talk about the Dijkstra algorithm. This is one of the very famous algorithms in the graph theory in computer science where we find the shortest distance between the two places. The algorithm, I assume that you already know about the graph theory, and in this video we will try to cover following a Dijkstra algorithm for the weighted and unweighted graph, the assumptions in the Dijkstra algorithm, and are there any better algorithms than a Dijkstra algorithm? So let's begin. Let's start with the problem here. Suppose we want to go from San Francisco to San Joseph, and we want to reach there as quickly as possible. That me and assume that there is no traffic. So that leads us to the shortest distance problem, and let's try to solve it. Let's first formally define the problem. Given a graph G and a source vertex S, determine the shortest path to vertex V. This is also called one vertex shortest path problem. So going back to the previous problem, we can say that vertices can be places. So that means San Joseph and San Francisco can be both nodes in the graph, and edges are the driving distance between the places. So let's look at the example here. We have a graph with four nodes, A, B, C, and D. As you can see, it's like a weighted graph. So that means there are different weights between the nodes. And then now to reach to point D from point A, we have multiple options available. Either we go to point B first and then to D, so that results in 7 as a distance, or we go from A to C and C to D, so that also results in 7 as a cost, or we can go to A to C, C to B, and then B to D, so that's like 6 in terms of total cost, and that actually is the shortest path. So today we will look into a Dijkstra algorithm which will actually help us solve this. But before going there, let's talk about the shortest path for the equal weight graph. So that's where we can actually use breadth first search, which is like equivalent of the Dijkstra algorithm or the special case for the Dijkstra algorithm. So the way breadth first search works is that we actually go through the breadth of the graph, meaning that when we are at a particular node, we go around the neighbors of that node until and unless we have covered all the and we continue this process until unless we have covered all the nodes in the graph. So let's take the example of this graph. We are at source vertex A. The neighbors of this graph are A and B. So that means they have the distance equal to 1. Then we go, so the neighbors of A, B, and S are C and D. So we again move to them. So the distance to them will be equal to 2. And then finally we have E as a neighbor to both C and D. So either way the shortest distance will be equal to 3. This is how the Dijkstra algorithm works for the equal weight graph, but this is actually the breadth first search. What about the weighted graph? So there we will need help from Dijkstra. So this algorithm is very similar to the Prim's algorithm, where we generate shortest path tree instead of minimum spanning tree. But before going there, let's know about Dijkstra himself. He was one of the most influential members of computer science founding generation. Among the domains he worked on include algorithm design, programming languages, program design, operating system, distributed processing, and I don't know what not. He was one of the geniuses in our field. Let's look at the pseudocode which we will be looking into the way we are solving the problem. So let's assume that X is a set of vertices which include assume that we have found the shortest path correctly. So it acts like a mold which actually grows over the time as we progress with the algorithm. A of S is the shortest path computed for each vertex. A of B actually will be the shortest path which we have shortest distance actually which we have got to the vertex V from source S. and then B of V is like a um, set of points which include the path, shortest path from source to the vertex V. And now let's move into the algorithm. So the algorithm starts with initially we have source vertex S, so x is equal to S. A of S is equal to 0 because the shortest distance to itself will be 0, and B of S will be the empty path because there is no path between the source to itself. Now we enter into the main loop. So the loop works till the point we have not covered all the vertices. So x is the set of vertices, v is the set of all vertices, e is set of all the edges. And now when we are at vertex w, and we are where it's not part of x yet, but it's part of v, and vertex v, which is actually part of x but and was part of v earlier. We choose the minimum edge between v and w, which such that it minimizes a of v and the length of the edge vw. So this is called the Dijkstra's greedy criterion. Once we satisfy this condition, we add w to x. So that means this vertex is now being conquered, and we have increased our mold x to the new vertex. We also add the shortest distance now for this node w to our set A, as well as to set B as the shortest path. I think this will get clearer once we take the example. So suppose this is our graph. Now we have 4 nodes in it, S, V, W, and T. The weights are already given in the graph. Now initially, like we said, A of S will be equal to 0 and B of S will be equal to 5, which is equivalent to null, I will say, because it's an empty set. Now moving forward, we have two options: either we take S or V, or we take S or W as an edge. So here we can see that S of V is shorter, and we apply the Dijkstra's criterion, and now A of V is equal to 1 and B of V is equal to SV, because that's the shortest path we have taken from S to V. Now we have 3 edges available. Either we take S to W, which is a weight 4, or we take S V of W. So that means we have to add A of 1, which is 1, and V of W, which is 3, or we take V of T, because this is also the new node which we can cover, but the score there will be equal to 7. So again we apply the Dijkstra's criterion, and we take the node with the edge which is the shortest score. So in this case it is 3. So we now have A of W equal to 3, B of W is equal to SVW, because that's how we will come to W in the shortest path. Now the last node is equal to T, and now we can either choose, the score will be either we reach there from W to T or from V to T. So we have already seen that V to T score is 7, but W to T score is equal to 6. So that's why our final point to reach there will be equal to T. So A of T will be equal to 6 and B of T will be equal to SVWT. So that's our shortest path. And hope this example clarifies how the Dijkstra algorithm works. Now, what are the assumptions in the Dijkstra algorithm? Dijkstra algorithm does not work for the negative weights. And why doesn't it work? Because suppose you have the edge weight with negative weight equal to -10 and all the other edges are positive. Now you add 10 to all the edges so that all the nodes are positive again. All the edges are positive again, but this will simply not work. So suppose from A to B there are 2 edges in one graph, and between A to B there are 7 edges in another graph. So this means that you added 20 in one of the graph and 70 in the another graph, and that means this algorithm cannot be applied greedily, because now you are not even getting the shortest distance correctly. Uh, so that's why it will not work. So to solve this, we will use the algorithm called Bellman-Ford algorithm, which is like a dynamic programming problem, which we will cover in some days from now. Uh, and then we have this question which all the computer scientists always ask: can we do better? And answer is yes. So as you would have noticed, when we were applying the Dijkstra's greedy criterion, we were choosing the minimum edge. So that should ring the bell that okay, we can use min heap, or we can use priority queue to do that, and that will actually speed up our algorithm afar, because we don't have to revisit B of W, which we are using for the bookkeeping there. Also, uh, what about when we have more information in the graph? For instance, suppose in India we are driving on the left side, so we would like to penalize the right side of the wing. So how, or we are in US or Europe where we are driving on the right side and we want to penalize the left turn. So can we do that in the Dijkstra algorithm? I will say maybe in a complicated way where we have to adjust the weight using some what do you say heuristic. But the better solution to use there will be the A star algorithm, because now you have the heuristic function which you can work with, and then you can, and this can be used by self-driving cars when doing the mapping, when they are navigating through the city, that okay, penalize the right side or the left side depending on the situation. So I think yes, we can definitely do better. Hope this video helped. Thank you so much, and please share the feedback or doubts on the comments below. Thank you again. Have a good day.